All right. So a couple of you guys had questions about number 13 on the Pearson assignment. So this is number 13. At least part A. I got asked about part A. So I'm just going to do part A for you guys. If you have questions about any of the other parts, send me a Schoology message or we can just deal with it on Friday, whatever works for you. So we have a circular loop of flexible iron wire, initial circumference of 166 centimeters, but its circumference is decreasing at a constant rate of 13 centimeters per second due to a tangential pull on the wire. The loop is in a constant uniform magnetic field of magnitude 0.8 Tesla, which is oriented perpendicular to the plane of the loop. Assume that you, get rid of this? Yeah, are facing the loop and the magnetic field points into the loop. So real quick, before we jump too far into it, just let's draw it out real quick. So we have a loop, we have magnetic field going into the loop. And the loop's circumference is decreasing over time, right? So in however many seconds, it will be like this, I don't know, whatever, right? So it goes from wider to narrow. We are obviously changing the area and therefore changing the flux, right? As our loop goes from bigger to smaller at a rate of 13 centimeters per second of the circumference. So this is what we're dealing with. And the first question is to find the EMF. Right? We want to find the EMF. So we just got today an equation for EMF, right? The equation for EMF is the absolute value of change in flux over change in time. All right. So this is the equation we're going to basically be trying to work with, right? We want to figure out, okay, what is the change of flux over time? Now, the problem is this equation for flux, right? What is the flux equal to? Because if we can't define the flux, we're going to have a hard time defining the EMF. So let's define the flux, right? The flux is equal to the area times B times the cosine of the angle between them. This problem is nice because it says they're perpendicular to each other, which means cosine is, perpendicular to the plane of the loop, which means the area vector and the magnetic field are parallel. So cosine is 0, that goes to 1, and we just get A times B. So the flux is going to be equal to A times B. All right. Area is changing, right? So we have to rewrite area. We can't just write area. It's area that's varying. So we rewrite area as pi r squared times B. And then we get another problem here because we're going to have to write this in terms of changing circumference, right? It's the circumference that's varying. And what we're given is the rate that the circumference varies. So it's not even really helpful to write area in terms of radius because we don't know how the radius changes. We know how the circumference changes. So I'm going to rewrite radius in terms of circumference. So we know circumference is 2 pi r, means radius is circumference divided by 2 pi. Okay, so we can plug that in there, right? Our flux, right, magnetic flux, I guess I should write an M on all of these because we're talking about magnetic flux, is going to be equal to pi times circumference squared over 4 pi squared. Sorry, I squared the bottom, right? The whole radius is squared, so the top gets squared, bottom gets squared, times B. Pi can cancel with one of those and one of those, which gives us flux is equal to, I'm going to pull the constants out front. B over 4 pi times circumference squared. Okay, so we get magnetic flux is equal to B over 4 pi times the circumference squared. Now, our circumference changes with respect to time, right? The circumference with respect to time is going to be equal to the original circumference, which is this 166 centimeters, minus the rate of change of the circumference, which is 13. So we'll just write that as a rate of change. It doesn't matter what. I'm doing this generally to start. So instead of just putting in 13 here, let's put in a value for that, right? Or a variable for that, maybe alpha, right? So this is alpha is my rate of change. Right, so alpha times time, right? Our circumference is going to be equal to the original circumference minus the rate of change times the amount of time that has happened, right? So in this 6 seconds or whatever, right, it says, that was the second part of the problem. It wants us to find the EMF after 6 seconds. I forgot to write that part. Right, so we want to know the circumference after, or the EMF after 6 seconds. So this would be 166 minus 13 times 6, right? That would give us the circumference of the current circumference of the circle. All right, so we can actually replace that in here as well, because it's not just circumference, it's circumference with respect to time. So our magnetic flux is going to be equal to B over 4 pi times original circumference minus rate of change times time squared, right? That is our entire equation for the flux. All right, so now we have to take this equation that we just got for flux and plug it back into our EMF equation, right? Because we've solved for flux now. We know flux is going to be equal to the magnetic field divided by 4 pi times the original circumference minus the rate of change times time squared. So we get the EMF is equal to the absolute value of B over 4 pi times, oops, I forgot the DDT. DT of B over 4 pi times C original minus rate of change times time squared. Absolute value. All right, so we're taking basically what this says, right? We want to take the derivative with respect to time of this entire function. And we can pull some constants out, right? Let's pull some constant out to make this easier. I'm even going to drop the absolute value sign for a little bit. I guess we don't have to, but I'm going to take out the B over 4 pi, right? We'll pull that out. That's a constant. Everything else isn't, though. So it'll be this times the derivative with respect to time of original circumference minus rate of change times time squared. And we actually, right, we're taking a derivative here. We have a chain rule, right? Multiply by 2 times the inside times the derivative of the inside. Right? I forget how they actually write the chain rule in math class, but it's essentially 2 times the entire term, whatever you want to call it, times the derivative of the term. So we'll get B over 4 pi times 2 times original circumference minus alpha times t, rate of change times time, times the derivative of the inside. The derivative of the inside, original goes away because it's just a constant. T, derivative of alpha times T is just alpha. So we get left with the rate. Right, and here we have our expression that we can plug in our known values to. We could simplify a little bit if we wanted to. I'll put the absolute value bars back on there. But 2 simplifies with a 4, right? We could make this just a 2 on the bottom. So cross that out, make this a 2 on the bottom. But then we can plug in all our numbers and solve. So our EMF is going to be the absolute value of, actually, oh, I almost messed this up. This is a negative alpha. Just, right, if we're being strictly doing the math correctly, that should be a negative alpha there. So that becomes negative alpha. B is 0.8 divided by 2 pi times original circumference is 1.66, right? We got to convert from centimeters to meters, minus 0.13 times 6 times negative 0.13. And I think if we do that math, it should check out and give us the EMF of 1.46 or something like that. Do I have it here still? Yeah, absolute value, negative 1.46 times 10 to the negative second. Absolute value means the negative goes away. So we just get 1.46 times 10 to the negative second volts because we are solving for an EMF. Let me just double check and make sure that math checks out really quick. 0.13 minus or times 6, 1.66 minus second answer. So we get 0.78. 1.66 minus 0.78 gives us 0.88 multiplied by negative 0.13. That's a 0.13 multiplied by negative 0.13. That'll give us negative 0.1144. Then we multiply by 0.8 over 2 pi. And we end up with negative 1.46. Sorry, negative 0.0146, right? We rewrite that in scientific notation, gives us negative 1.46 times 10 to the negative 2 volts for our EMF there. All right, so that's part A. If you have trouble with the rest of it, we can talk about it on Friday, or you can shoot me a Schoology message or something like that, and we can go through it. All right.